Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is lecture 19. Today we're going to cover a little more about the exponential distribution, and I want to really hammer home some of the parallels with the geometric distribution. And then we're going to lead into a lecture that's maybe a little informal, but which I like to call the CDF trick. So today's topics include the parallels between geometric and the exponential distributions, and what also I'll call the CDF trick. Which essentially points out that, especially when you're looking at continuous random variables, and suppose you're trying to determine the probability distribution that's involved here, you want to know the PDF. Often it's easier to actually work with the CDF and then differentiate to obtain the PDF. And so I'm going to point out a couple of situations where this happens, again, trying to tie back some material from the previous two lectures. So let's start off with this sort of parallelism between geometric and exponential distributions. All right, so let's go ahead and get down to it. So let's recall. When we first considered the geometric distribution, remember this was in the context of discrete probability. And one way in which we defined it was the number of tries needed to obtain the first success. I want to point out a slightly different way of formulating that problem, which is used, and you might also see either in textbooks such as Pittman or on the internet. So there are sort of two formulations. One was saying, let's say the probability of t equals k is the probability that you need k tries to obtain your first success. And this worked out to be something like q to the k minus 1 times p, which you can also think of as one minus p to the k minus 1 times p. And this, again, makes perfect sense. We're trying something independently where each success doesn't depend on what happened before. And we're just saying, well, first I have to fail k minus 1 times, and on my kth try, I finally succeed. So the second formulation views counting the number of failures as actually the more important quantity. So another way you can think about it is the probability of, let me call this G. Well, let me say F actually. F equals K equals the probability that you fail K times before succeeding. This is actually a pretty elegant formulation. And the formula is going to look very similar to what you have normally, except that we're now going to increase from k minus 1 to k. So here, this is your probability mass function for the ordinary geometric. So I'll call as the ordinary geometric. Here we have something that's a slight variation on that, which says that you have to fail k times and then you succeed. So it's q to the k times p, which equals 1 minus p to the k times p. And so this is sometimes just called the PMF for the geometric p distribution. And ultimately, you can work with either one, although some formula is going to be slightly different. For example, if you go back into Pitman here and you go at the distribution summary section, it's going to give you the sort of two different settings where you might look at what is the geometric p where the distribution is, right, yeah, good. So you'll have one situation where, boop, 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 you can see geometric p back here in this table. And I'll just go ahead and write down, for this distribution, we already know that the expectation of t, my apologies, is 1 over p. And the variance here equals q over p squared. For this one, things are slightly different. The expectation of f, which we still think of as being geometrically distributed, looks like q over p. And the variance here looks like the same thing as essentially q over p squared, which makes perfect sense because variance measures deviation about the mean squared. And so if you shift everything up or down by a single unit, it's not going to change anything. This kind of fits into our understanding of linearity of expectation. Anyhow, I want to point out a quick parallel with how this matches with what we know about the exponential distribution. So here we go. We have slightly different formulas. For expectation, but the variance is the same. And again, the difference here, if you want to think about it, is this has a range or support up here. It's the set of integers 1, 2, 3, on up through infinity. Whereas here, the support looks like 0, 1, 2, 3. So the only difference is that it includes 0, whereas this guy does not include 0, which is essentially saying, well, you got to try at least once. Maybe there's a moral there. Anyhow, important thing to remember is, again, geometric is the process that you want to model if you are counting something with a discrete number of tries. It's a discrete random variable. Exponential, on the other hand, is continuous, so meaning that the range of possible outcomes is continuous. So I'm just going to say that notice so if I do f, which is my geometric p distribution, has support, and this is the places where the probability is non-zero. let's say k, where p of k is not equal to 0, support equal to 0, 1, 2, 3, just those integers, but on all the way off to infinity. Now let's compare this with the exponential. And so, you'll recall that the graph of the exponential distribution looks something like this. It was a 0 up until we got to t equals 0, but then at 0, the PDF, which I'll call f of t of little t, is equal to lambda e to the minus lambda t, for t greater than or equal to 0. So in particular, if you plug in t equals 0, you're going to get something that's non-zero. In particular, you're going to get equal to lambda. Now, this actually, and again, remember that this represents probability density, so you need to integrate in order to get probabilities. There's a lot of things that make this formula look similar to what I just wrote down with the geometric P distribution. And I want to also remind you that we've got the following facts about this. So here's facts about exponential. One is that the expectation of t, where this is our random variable that's governed via lambda, is equal to 1 over lambda. And the variance of t is 1 over lambda squared. So in particular, the standard deviation of t is 1 over lambda. These actually match. So expectation and standard deviation end up being the same for an exponential random variable. Let's go ahead and just do a quick comparison of where does this formula come from. So if you think about what's happening on the geometric side, we've got, let's say, again, F, this is when we count the number of failures. You want to think of this as, let's say, Q to the K times P. Now, I want you to think a little bit more like a physicist here. So Q is the same thing as 1 minus P. I'm raising that to the kth power, and then multiplying that by P. If I use my 1 minus x is approximately e to the minus x approximation, then I end up obtaining that this is the same thing as e to the minus p times k times p, which suddenly should look a lot like the formula e to the minus lambda t times lambda. Basically just need to match and say that p is lambda, and then you'll get the same formula, and that k is t. So with, let's say p equals lambda and k equals t. And moreover, this analogy extends to looking at some of the properties of these distributions. So if you look at, let's say, the expectation. So again, it's just as a recollection, when I looked at exponential of f, this looked like q over p. So it looks a lot like the ordinary geometric, except you've got this somewhat pesky factor of a Q sitting up top. All right, that's fine, but let's go ahead and just think about this again. So as a physicist, so this is the same thing as 1 minus P over P, which is the same thing as 1 over P minus 1. Now, you want to think about this process as being where P gets really small, where we've like subdivided our notion of atoms of time so that the probability of a failure occurring in a given window, or you think of it as a success, is very small. So this actually 1 over P. So if P is very small, then we can approximate this. Then we realize that is very large. And so we can in effect kind of cancel or forget about this term here. So in particular, the upshot being that the expectation of F is sort of approximately 1 over P. So again, if we do this sort of substitution of P equals lambda, now we get 1 over lambda, which is the expectation of T. And of course, this goes down a level as well. So if you consider, let's say, the variance of our geometric, we already said that this is Q over P squared. So if we run the same analysis, 1 minus P over P squared, then 1 over P squared minus 1 over P. Then we end up in a situation again where if P is very small, then 1 over P squared dominates. And so we can say that this is roughly 1 over P squared, which again looks like our 1 over lambda squared that we had up here for the variance of an exponential random variable. So this sort of analogy goes actually pretty deep. And I'll even intimate that this notion of a half-life that we've been talking about with exponential random variables, which again shows up in a lot of chemical processes. We can think of radioactive isotopes decaying. When has 50% of the material decayed? Or when do you think the probability of a machine breaking has exceeded, let's say, 50%? After what period of time? This kind of half-life analogy actually was supported in something that we can see more clearly in a discrete setting. So if we consider an urn where I've got, let's say, 97 green balls, and I have, let's say, 3 red balls, then I can have the following experiment. Suppose I draw out balls one at a time with replacement. After how many draws do I have less than a 50% chance of seeing no red balls? So what does this amount to? Well, it really amounts to the following question, which is probability of no red balls in draws is equal to 1 minus 3 over 100 raised to the n. And so what we're trying to do is find when is this less than a half. Obviously, because 1 minus 3 over 100, which is the same thing as 97 over 100. That's what this whole formula equals. Obviously, since 97 over 100 is less than 1, if I keep raising it to some power of n, higher and higher powers, this is going to go to 0. So there has to be some value of n where this ducks underneath a half. Now, how do I find that? Well, you could do some tricks, but again, if we're thinking like a physicist, we should imagine we have this exponential approximation. And we want this to be less than a half. So sorry, that's 3 times n. Make this clearer. Minus 3n over 100. And so the same thing says that if I take natural log of both sides, then I have minus 3n over 100 is less than negative natural log of 2. Now again, multiplying through by negative 100 over 3, we end up getting that's n has to be greater than 100 over 3 times the natural log of 2. Now again, notice this right here is, this is actually our expectation. This is our expectation of a geometric random variable t, where we count for number of tries until we get our first red ball. And so then that expectation weighted by log of 2, which essentially cuts this down to 0.69 of what we have, ends up working out to being, check so I can give you a precise number. Yeah, 23.1. So you can kind of think of this as the half-life of this discrete problem. And notice again that when we think of this expectation as a sort of quote equal to 1 over lambda, then we have exactly the median formula. Which is natural log of 2 divided by lambda. Exponential distribution. So this is, again, very fruitful things to think about, maybe a little more deeply. One final thing I want to note is this memoryless property. So final connection. So in both the geometric, and it doesn't matter which flavor you want to use, you could say F, counting the number of failures, the probability of failing, or your first success happening after K failures, or A plus B failures, given the information that you've already failed A times, this is equal to the probability of F greater than B. Again, on the exponential side, we had that the probability that t lasts beyond some little t plus s, given that some amount little t of time has already gone by, is also the same. Oh, yes. which kind of gets at this idea of if a machine part is governed by an exponential process, then if it hasn't broke yet, it's as good as new. So maybe you don't want to change your water heater because it's still working, so it's as good as new. Okay, so that's enough for the parallels between geometric and exponential, and I just wanted to kind of remind everyone of that. Let's look at some other problems related to the exponential, which now moves us into our sort of CDF trick. And so I'm going to start with a concrete question. So all right, so how does this CDF trick present itself in practice? Suppose you're asked the following question. So suppose I buy 10 light bulbs, each of which have an average lifetime of 1,000 hours. What is the expected time of the first failed light bulb? Here we're assuming each lifetime of each light bulb is some, let's say, xi, which is exponentially distributed with some parameter lambda, which we know has to equal 1 over 1,000 hours because of this inverse relationship between average and lambda. All right, so how do we get at this? So what's confusing here is that we've got a whole bunch of exponential random variables. In fact, we have 10 of them. So we have x1, x2, on down through x10. And each of these are governed via this 1 over 1,000 hours parameter. There are IID exponentials where, x1 is the first light bulb's probability, or let's just say lifetime time of failure, on down through x10, which is the 10th light bulb time of failure. Let's take a quick moment to comment that before, when we were talking about the geometric, we always said, no, how many times you have to fail before you succeed? Our language, we can always swap out success and failure, right? Maybe you're used to succeeding all the times. Now you want to know, well, what's the expected time to my first failure? That's actually the language we use for exponential random variables. I've got a light bulb that's alive, working, it's succeeding. And then I'm asking how many time steps needs to go by until it finally fails, bites the dust. Now, what makes this problem complicated is we can't just average these random variables because we know that that average is going to work out to be what we'd expect, the normal 1,000 hours. What we're looking for is what's the time of the first failure. So that means even if I have this like distribution of failure times, the value is governed by the earliest failure. Now that earliest failure is the same thing as the minimum. So what we want is, let me call it M. So define M, which is a new random variable. And this random variable is going to be defined as the minimum of this collection of random variables. It's the minimum of x1, x2, all the way up through x10. Yeah, because this is what we want. Is first, i.e. earliest failure. Which means the minimum amount of time has gone by. So you're looking for the minimum of each of these values. So how do we find PDF of M? Because this is now a new random variable. And in order to compute its average, its expectation, I need to figure out what is the probability distribution for M, my minimum random variable. And it turns out we need to first consider the CDF, or that's going to be the thing that is the easiest to handle. So this is the motivating question. All right, let me go ahead and just start a fresh page here. So let's see. So we're going to say, consider CDF. And again, this is the thing which when you integrate, it approaches 1 as a value because the total probability has to go from 0 to 1 eventually. So recall that given any, and I mean any random variable, x, and if you either use the probability mass function or the PDF, we can define f of, let me call it t, to equal the probability that x is less than or equal to t. Now, in the continuous case, this is the same thing as the integral from minus infinity to t of, whatever that PDF's distribution is. And I'll just use s as a dummy variable in this case. Now, some people say density or distribution function. So yeah, that's where the CDF comes from, cumulative density function. So what happens if I try to apply that to our problem? So let's apply that to our problem. All right. Well, again, it's one of those situations where it's probably easier to work with a complement. So computing probability that m is less than or equal to t is hard. computing, let's say, the excess or remaining density function, so probability that m is greater than t, it actually turns out to be easy, because all I'm saying is that the minimum value has to exceed t. This formula here asks one of the values has to be less than t, but you don't know which one, and the other ones can be anything as long as it's greater than that. Working with this condition actually turns out to be easier, because I know that every random variable has to be greater than t. It is easy. Well, why? Well, this ends up being the same thing as the probability that x1 is greater than t, and x2 is greater than t, and x3 is greater than t, all the way up through x10 is greater than t. Now, again, by independence, so I can apply independence, I can say that this is the same thing as the probability of x1 being greater than t times the probability of x2 being greater than t, all the way up through the probability of x10 being greater than t. Now, each of these probabilities that the failure hasn't happened yet, this is also sometimes called the survival function. And if you remember, we computed directly the formula for this. It looks like e to the minus, let's say lambda 1 t times e to the minus lambda 2 t, all the way up through e to the minus lambda 10 t. So in particular, you didn't even need to assume that each of these 10 light bulbs had the same expectation. Could have bought some like crappy light bulbs and then some really nice ones that are supposed to live a long time. So right now I'm just giving us the more general formula right here. We'll make that 10 a little more transparent. Now, what is this? Well, this is the same thing as e to the minus lambda 1 plus lambda 2 all the way up through lambda 10 t. And so consequently, the CDF of m, which equals the min of x1 through x10, where each xi is distributed according to some exponential with parameter lambda I, well, it's going to be 1 minus this thing, right? So 1 minus, let me write it down. Oops. So this is a capital F of m, that's the CDF. T is going to be 1 minus e to the minus lambda 1 up through lambda 10 times t. And by the fundamental theorem of calculus, I know that I can recover the PDF, because that's what sits inside of the integrand here. Remember, so if I differentiate capital F of t, I'll obtain little f where this limit is inside. So this just expresses the idea that integration and differentiation are inverse to one another. So if you have integrated something, but you want to undo the integration process to get the function that you were integrating, you could just differentiate the integrand. So taking ddt of fm of t gives us little fm of t, which is lambda 1 up through lambda 10, e to the minus lambda 1 plus lambda 10 t. This is the PDF for m. Is actually another exponential, but equal to the sum of each of the parameters that govern the individual lambdas. Now, what is a practical consequence of this? So we need to finally answer our question. So now we have answer to our question. What's the average time of the first failure Well, it's going to be one over lambda 1 through lambda 10. So in particular, when each lambda 1 is equal to lambda 2, they all have the same expectancy of 1 over 1,000 hours. Then this expression actually collapses down to it's going to be 10 over 1,000 hours, which is then in turn going to be 1 over 100. So in particular, if I plug that in back to this formula, it's going to end up being 100 hours is our expected time till the first failure. And so this is really, fascinating because you'd almost think that, all right, I've got 10 light bulbs, each of which are supposed to last 1,000 hours, but somehow like the time that will pass until you need to replace one of them actually has gone down by a factor of 10. In fact, here's a little important upshot. So if you had 1,000 1,000-hour light bulbs, then you'd expect to replace one every hour. And so this definitely happens for people who like work on Broadway or in theater, and they have to do really intensive lighting setups. You have tons of light bulbs. And so just the probability that one of them is going to fail soon increases, and in fact increases proportional to the number of light bulbs that you have. So the amount of time that you have until you have to replace something ends up becoming increasingly short. All right, so that was one trick, and I'll remind you that one example of the CDF trick. Let me go ahead and remind you of another one, and this is supposed to be really quick. So here's another example. Remember when we wanted to determine the time of second arrival, or you could think of this as maybe failure in a Poisson point process. What we ended up doing was first computing exactly what we did up here, which was let's compute the probability that our new random variable exceeds a certain time t. So this is 1 minus the CDF. So if we work with that question instead, things are slightly easier. So the probability that the second time arrival happens after time t means that this is the same thing as the probability of 0 or 1 arrivals in 0 to t. And this, in turn, turns out to be the same thing as asking, well, what's the probability that n, which was our counting function associated to this interval 0 to t, equals 0 or 1. And this was in turn a Poisson random variable. With lambda t as our parameter. Instead of just ordinary lambda, because we got time involved, we need to take the formula for the Poisson distribution, and whenever we saw lambda, substitute lambda t. So this is the same thing as asking that, all right, so let me take it lambda, lambda t to the 0th power over 0 factorial e to the minus lambda t plus lambda t to the 1 power over 1 factorial e to the minus lambda t. All right, remember, that's just the Poisson where wherever we had lambda in the discrete setting, we're now actually using lambda t. And so then we took the derivative of this, or now we got the CDF. So it means that the CDF for T2 equals the probability that T2 is less than or equal to T is now 1 minus this expression. We call this star. It's 1 minus star. So then to determine the PDF, we just had to differentiate. So PDF equals the derivative of the CDF. And consequently, we got that the probability density function for the time of second arrival was like lambda squared t e to the minus lambda t, which you can just double check for yourself. By differentiating the expression above. And if you sort of buy this, this derivation, you end up deriving sort of the formula for what's called the gamma distribution. So we'll call gamma r lambda was equal to lambda to the r, x to the r minus 1, e to the minus lambda x divided by gamma of r, where gamma of r is equal to this integral from 0 to infinity of x to the r e to the minus x dx, which coincides with r minus 1 factorial when r is an integer. Gamma function is just the continuous extension of factorial to any non-negative number. We're going to see this pop up shortly in another example. And I'm going to put this under a broader heading here. So this is this goes underneath the heading of understanding functions of a random variable and their PDFs. Now, there's good reason to believe that this happens all the time. We've already seen situations where, one number is governed by some random process, but then now we want to perform some operation with that number. Maybe pass it through a polynomial. Easiest example of a polynomial that's not, just the identity would be like x squared, which also kind of comes up when we try to compute things like, the variance. We do the expectation of x squared. Although in that case, things tend to be slightly easier. Let's focus on this example and let's consider a different random variable because we've been talking a lot about exponentials. So let's consider some random variable x that is a unit normal. So that means it looks like, this guy right here, it's PDF. X is e to the minus x squared divided by 2, square root of 2 pi. That's our little f of x, little x. This is our unit normal. So mean equals 0 and variance is equal to 1. In all the calculations we did with the central limit theorem, we were basically providing some sort of transformation that put us in this situation. Let's consider a new random variable, which is just x, but then we square it. Now, remember, in this case over here, this right here is 0. So sometimes, indeed, 50% of the time, your numbers are going to be over here, which is negative. So then squaring it's going to turn that into a positive number. So this process of y equals x squared kind of folds over the distribution across this axis, and that's gonna change the shape of this curve that governs the probability density of y. But what is a formula for it? How can we actually find a formula for it? Well, again, sometimes it's easier to work with the cumulative situation. So let's compute the CDF. That's going to be the answer. We're always going to try to compute the CDF and for this continuous case. All right, so what does that mean? I need to find the probability that y is less than or equal to some little y. But that's exactly the same thing as asking the probability of x squared is less than some value, little y. But, if you think about it a little bit more, that's the same thing as asking that x be between minus square root of y and the positive square root of y. Right? So that basically covers all the ways in which x can produce a square that's less than y. It can either be all the way up to negative y square root of y, or it can be up to positive square root of y. But in all those values, you're going to end up squaring to be less than some number. Now, luckily, this is something we've considered a lot. We have these sort of special formulas in terms of the CDF for of this normal distribution, which we called capital phi. So we have square root of y minus square root of negative y, which by symmetry we know actually equals this. This is just an argument specific to the normal distribution. You can't do this for just any random variable, but you can do it for the normal. And so now that we've found the CDF, this is the CDF, we can differentiate it. So now differentiate. Well, let's get to it. So let's take d dy of this expression. So of this, so 2 times capital phi square root of y minus 1. All right, derivative of a constant, 0. So now we're just left with 2 times the derivative of capital phi square root of y. But remember, what was capital phi? Well, capital phi was the CDF of the unit normal, which we also sometimes call little phi. So if we differentiate this, we're going to end up getting back to little phi, but with value square root of y. But then we also need to use the chain rule. So we now get something like 2 times little phi square root of y. And then I need to take the derivative of the expression inside. So d dy of the square root of y. And so this ends up giving us 2 phi square root of y times 1 over 2 square root of y. And we got a little bit of cancellations going on here. And so we end up getting little phi square root of y times square root of y. Now let's go ahead and just write that out fresh. So for x, a unit normal, and whose PDF consequently looks like phi of little x, 1 over square root of 2 pi e to the minus 6 squared over 2. For y equals capital X squared, we don't know how it's distributed, but we just computed its PDF. Its PDF looks like phi of square root of y divided by the square root of y, which if I just plug in to this formula right here, ends up giving me 1 over square root of 2 pi times y. So now I've got a y down there. And then e to the minus, well, x squared, when x is square root of y, is just going to give us back an e to the minus y over 2. And it turns out that this actually fits into this family of gamma distributions where you put r to equal 1/2 and lambda to equal 1/2. And let's just think about that for a second. So when r is a half, I have a half minus 1. That's going to mean I'm going to have a 1 over square root of x down in the bottom here. And if lambda is a half, then that's already 1 over square root of 2 pi. So if we know the extra bit of information, so if we're given that gamma of a half, which this is a half factorial, whatever that means, is equal to the square root of pi, you can then say that this just squaring a normal now gives you this weird distribution evaluated at these parameters. So that just shows you that even though this gamma distribution might seem, like where did it come from? It actually comes from a lot of distributions, but just by plugging in different values. So they're all part of the same family. And in particular, we have this sort of observation that we can observe that x squared for x a normal and an exponentials all fit into the single family of gamma. It's kind of nice. Now that may have been a little, fast, especially for those of you who haven't, practiced with the chain rule in a little bit. So let's look in a situation where the chain rule looks a lot simpler. And one situation in which this occurs is when we're looking at a linear function of a random variable. So we have linear. Some people will say affine. Functions of a random variable. So imagine y is, instead of x squared, it's just ax plus b, where x is some random variable. Let's compute the CDF for y. So again, remember what this means is I need to compute the probability that y is less than or equal to some little value, little y. Now, all you need to do is just sub in y equals ax plus b. And now you just need to massage this expression a little bit to get what are the constraints on x. So it's the same thing as a probability that x is less than or equal to y minus b divided by a. Again, just by subtracting b from both sides and dividing by a. So in particular, if you already know the CDF of x, let's call that capital F of x, then this is the same thing as y minus b over a, where this is the CDF for x. So in particular, if I want to determine the PDF for y, so now I need to differentiate. Well, now I can just say that little f of y is going to be d dy of capital F of x evaluated at y minus b over a. And so again, by the chain rule, well, I just take the derivative of the outside. So maybe to use notation that's slightly more familiar, f of x prime evaluated at y minus b over a. But then I need to take d dy of whatever's inside. And so the constant's not going to matter, but that y times a actually does matter. And so just to sort of summarize, we end up getting that for a greater than 0, f of y ends up being little f of x of y minus b over a times 1 over a. Maybe just go ahead and put that in a little so that's the formula. Assuming you know the PDF for x, you can determine the PDF of y by just taking y minus b divided by a, plugging in the PDF for x, but then scaling everything by a. Let me just leave you with one more observation. So here's what I'll call the sort of final fact. I'll call it maybe the final formula. And it says something like this. So if X is a random variable with PDF little f of X, and G is some function is, let's say, differentiable with G prime of X equaling 0 only at finitely many values of X, then PDF for Y, which is going to be defined as G of X, is the sum over all X such that G of X equals Y. And again, I'm assuming that G prime of X is not equal to 0 at these points. I take the PDF of X, evaluate at these little X. So I look for X that satisfy this condition, meaning it gets sent to Y. This is like if I want an X that goes to something squared, then I need to take plus or minus those values. So I check that this holds. Times 1 over the absolute value of G of X. And this is going to be, this is the PDF for Y, which is G of X. And so just to show how this includes the previous example, if G of X equals AX plus B, or let's say A is not equal to 0, so that means there's some slope. Then this formula specializes to, well, I need to find the sum of X such that AX plus B equals Y. Let me write this out a little bit. So let's write this. So f of Y, little y, equals the sum over little x such that, well, AX plus B is equal to Y. And then I'm going to look at f of those X. And then I'm going to take this by 1 over, well, I need to take the derivative of this expression. But that's just going to give me A, and I need to take the absolute value. But what are the X such that this equation is true? Well, I can figure this out a little more. Well, this is the same thing as saying that X is equal to Y minus B divided by A. And in fact, there's a unique value that associates to each X this Y. The function's what's called one-to-one. So this ends up being the same thing as, so there's only one value. So the sum disappears. And we obtain instead f of Y minus B divided by A times 1 over A, which is exactly the formula that we had over here. But now we can work with even with negative slopes. And that just comes from the fact that the way this is going to accrue probability if it ends up being negatively associated. means we end up having to switch a sign when we're doing the derivative. But at the end of the day, it ends up not mattering. And that not mattering is reflected by the fact that we put absolute values around it. All right, so thank you for your attention. I look forward to seeing you in class soon.